Yes, thank you very much, Matthias, for the introduction. And of course, also a warm welcome from my side. We are very glad to have such a good resonance on our topics of ET2SMEs. And yeah, as Matthias already said, AGET Regional Development Agency of Aachen Region, we are leading this project. I would like to give you, first of all, a very brief overview in 10 minutes what ET2SME is about and what are we offering. First of all, well, it's of course about the Einstein Telescope. I think most of you are already familiar with this really cutting-edge new research infrastructure of European and maybe even global importance. Maybe you can go further, Matthias. On this first slide, you just see some cornerstones about the investment that is connected with this new facility, about the jobs that are to be expected, and also the candidate locations. There are only two, and I think the more the process is proceeding, it is the perspective and chances are getting better and better for this cross-border region here. You also see the time path, which is heading further out than 2032, but as you can see from our activities and also from the various projects that we already now do concrete activities. What is the target of ET2SMEs? If you go to the next slide, you can see that we first of all want to inform and involve especially companies, SMEs, of this extended cross-border region of Belgium, the Netherlands, and North Rhine-Westphalia into this process of establishing the Einstein Telescope and let them profit. And more specific, what we want is to foster cross-border cooperation of businesses in the ET relevant technologies, in the instrument and also in the geology technologies. By doing or by setting up concrete cross-border innovation projects. To the next slide. What we offer via ET2SMEs is a kind of value chain, and you can see here the various elements of this chain, starting with mapping and ending up with sustaining what we are doing. I just want to give you a brief overview on what we are doing, and Catherine de Paap, the next speaker, will step a little bit deeper in various topics that are ahead of us now. The next slide. If we talk about mapping, we are talking about two different elements. The first, next slide, please, is about mapping the technologies. So what you can find here on the ET2SMEs.eu website is the so-called ET Technologies online catalog. You can see which technologies are needed, which technologies are addressed from this huge new research facility in the instrument, but also in the geology technologies. Click please once more. You can see that we have for each technology a short description. What is state of the art? What is needed here in terms of the Einstein Telescope? Which improvements are needed? What are economic perspectives? Which ongoing or future procurements will show up? So all these information are available via the website, so you can dive a little bit deeper here in each technology. Mapping, going to the next slide, means also a mapping of actors, mapping of companies, mapping of research and universities that are dealing with the Einstein Telescope. So we offer a new online platform also on our website, where all companies and all research actors can be present. So register via the website and present yourself. What we do is not only show the icons in a map, but also offer such an info profile where each entity can briefly display what they are doing, where they are, and what their markets are. So this is a very good and very easygoing opportunity to be present here on this new mapping tool. Next slide. Then going a little bit deeper, we are doing various visit and also networking activities. First of all, we have the various company visits that our partners, please to the next slide, are carrying out. So looking all over the cross-border region, the 4 different regions of North Rhine-Westphalia, Wallonia, Flanders, and also the Netherlands. We have carried out more than 180 company visits in the first year of ET2SMEs in order to talk one-to-one and explain what we are doing, what we are offering. And you can see also which different competencies we already have found out. The next. What we are also doing is participating in networking events, but also carrying out own events like this one here too. So you have the opportunity and will have the opportunity in following up events to get in contact with other companies. This year will be the last online virtual events. So starting from end of April, we will also go back to physical events. So where you really have the opportunity to get in contact with others. The next one. Very important is also what we're offering in terms of concrete business contacts and consortia building. What we are supporting is the establishment of project ideas, but also the search for project partners across borders. If you click please 1 or 2 times more, we set up meetings with potential partners, and those partners, of course, can also then apply for vouchers, apply for funding that we are providing. Next one. Well, the vouchers and the innovation projects, a little bit more concrete about that. We have so-called innovation vouchers, grants between 25,000 and 50,000 euros that we are providing for cross-border SME-driven innovation projects, a minimum of 2 companies from 2 sides of the national borders. And we have ongoing calls here. Here you see the one from February. The 3rd call is now currently going on. And going to the next slide, we can also announce that within the last days, the first cross-border innovation voucher was already granted. So we have granted the 50,000 euro vouchers to the combination of Yonek and Johnson Precision and Engineering. This project is the first one that is currently running. Others, additional ones will follow. Next one. And last but not least, I will close also with some sustaining activities. Very important that we are working on an industrial advisory board, which will have regular meetings of all ET relevant businesses and research entities of this enlarged cross-border area. This is also an opportunity pointing out already towards the running facility, so pointing out also beyond the ongoing projects. So this is really in a nutshell what we are doing. So if you have any questions, please refer to the different partners you can see here. Please refer to the website that I already mentioned, and you can find there all further information. So thank you very much for this first for this very first talk here. And I will now hand over to Katrin, who will step a little bit deeper into the different offers and different opportunities. Thank you very much.
Thank you, Ralph, for the introduction. All of you, welcome also from my side. And I want to thank you to be here, and also for the ones who will present. Thank you for your presentations. Now, in the next 10 minutes, I would like to address me to the companies, because I would like to tell the companies what's in it for them, what's in it right now, right here. What are the opportunities thanks to the Einstein Telescope? So that means that I won't talk about the future opportunities, like, for example, if the Einstein Telescope comes to this region, you can be a supplier for the Einstein Telescope. That's something for the future. Today, I want to focus on today. And I see, if you go to the next slide, please, I see 4 main opportunities that are the tenders, the vouchers, and networking, and that all leads to more visibility. So now I will, in this keynote, I will talk to you through these 4 elements, starting with the first, and that are the tenders. So Ralph already told you about the project ET2SME, but there are still 2 other scientific programs. It's the ET Pathfinder, which is a functional scale model of the Einstein Telescope. It's situated at the University of Maastricht. And the other, and for this audience, more relevant scientific program is the eTest, because there they're testing components, and they are also studying the geology. And we have some speakers in the rest of the event who will tell you more about the challenges and the situation on that matter. So both scientific programs write out different tenders. And you can find the tenders on the website. The link is on the slides, or just Google eTest procurements and you will find it also. There on that website, all the tenders that are announced or that are still to come are published, are lists, and the ones that are open, you can click on them and then automatically you come to a formal. If you go to the next slide, like something like that, where you can register and you can find all the specifications, drawings, details of the tenders that are open. And you can also make your bids there. So keep that in mind, that website, look at it and make your bid. And we all wish you a lot of success with it. That was the vouchers. Now we come to the vouchers. That were tenders. Now we come to the vouchers. And a big difference between the vouchers and the tenders is that for the tenders, you are a supplier of a scientific program. For the vouchers, it's all about your core business. So the idea is that your core business shall improve. So when you take your core business to the next level, when you create a new or an improved product, and so on, for all these ideas, you can have a voucher. And that voucher is up to 50%. And how does it work? Like Ralph already mentioned a bit. First of all, we hope that you are inspired by all the challenges and technologies of the Einstein Telescope. And then if you are inspired and you got an idea, it's up to create a consortium. If you click a few times further, yeah, thank you. So how does a consortium looks like? It has to be at least 2 companies. One of them should be an SME, because only the SME is eligible for funding. It also has to be a cross-border consortium. So that means a Belgian company with a German company, or a Dutch company, or a Dutch company and a German company together. Surplus, you can add, sorry, I'm from Limburg, that's not that fast. You can also add a third or fourth company or a larger enterprise or a knowledge institution to that consortia. Then you work to your project ID, and your project ID will be assessed. And the assessment criteria are ET relevant, so it has to be relevant, there has to be a link with the Einstein Telescope. Innovative, it has to be, your ID should be new or should be an improvement. And third, also market potential. That's a very important one, because the market potential is, like I said, it's about your core business. So it's not only providing something for the Einstein Telescope, no, it's about your core business, your market, or new markets that you want to address. And for that, you can give a voucher, if you can receive a voucher up to 50% with a maximum of 50,000 euros a project. So if the consortium are 2 SMEs, it's 50,000 euros max. If the consortium has 1 SME, it's 25,000 euros max. Then we are to the next slide, and that gives us to the last geographic condition, because I said it has to be an SME, but the SME must also be situated in the extended Euregio Meuse Rhine to be eligible. So that means for Belgium, the SME must be located in Limburg, Liège, Leuven, Roei, or Warem. For the Netherlands, it's Limburg, Zuidoost-Brabant, and for Germany, Aachen and the Eifel. So the location is a condition for the voucher, but it's also an opportunity for you, because it means that you can network internationally. And that brings me to the next slides and to the third opportunity for you guys. It's networking. Rolf also mentioned that. It's very interesting to network around the Einstein Telescope, because first of all, it's international, like I said, but second of all, there's also not only companies, but also knowledge institutions, and also the scientific criteria of that, and the scientists who work on it, and also government is involved. And you can all meet the stakeholders. Where do you meet them? Well, you meet them at our workshops, I suggest.
Last minute.
Okay, thank you. So here you see the different workshops that we organize, and I think that the most important for you is W3 and W5, because that's our geological elements. There is also the advisory board. If you see to the next slide, it's the 29th of April, and this is also a very nice one, because you can visit the ET Pathfinder, the functional scale model that is at the University of Maastricht. And that brings me to the last point, the visibility, and that's a very clear one. If you have a tender, you can go to the next one, Matthias. If you can have a tender, you can deliver products for a big science project, and that's a great image builder. Vouchers you can reach for new clients and new markets, and networking, of course, that increase your visibility. So for all of that, you can contact us, and we are happy to help you. Thank you very much. I will now hand over the presentation to Joseph Igmans, who will tell us more about big infrastructure projects. Thank you.
Okay, thank you, Katrien. Well, first of all, welcome to all of you also from my side, and thank you for the opportunity to talk a bit about managing and starting up big infrastructure projects. My name is Joseph Hickmans. I work for Tractable Engineering, and within the Belgian branch, I'm responsible for the tunnel projects in Belgium. Next slide, please. Oh, that came out a little bit different than I thought. I see the white dot has disappeared, so the text is quite difficult to read, I realize. But I will tell it. So Tractable, it's a global engineering company, and worldwide we have around 5,000 people, experts and engineers present. We aim for solutions in a carbon neutral and sustainable future where people, planet and profit thrive collectively. And we try to connect strategy with design, with engineering and project management. We are divided in 4 main branches, which are called urban, energy, nuclear and water projects. And next slide, please. Tunnel projects is part of what we call urban projects. So it's all related most of the time with transport infrastructure. So tunnel projects in general, well, specifically if you live in the region of the eastern part of Belgium and you have to go to the western part, most people here I think will know that it is quite a problem. You have to pass through Antwerp or to Brussels, and you're in trouble around Antwerp, around Brussels. So we see that infrastructure is becoming quite problematic. So it means that these last years there were also quite some investments done in tunnel projects to get traffic below ground. Some examples are the Oosterweel connection in Antwerp, in Belgium, but also in Maastricht. You have recently finished a few years ago the A2. We have North-South Kempen, Diablo project, etc. Many more. But they are all characterized by being a very complex environment. On the right-hand side of the slide, you see some projects achieved by Tractable, or Tractable was involved in that. So we did some new builds, some renovation projects, which I will not go into detail now. Next slide, please. So to come to tunnel projects in general, because we are here, of course, with the Einstein Telescope, and although aside from the magnificent concept of detecting gravitational waves, it is also, before you can do that, it's quite a project, and it's also a tunnel project, because we talk about 30 kilometers of tunnel infrastructure, 200 meters or something like that below ground. And so in general, tunnel projects, when we, in our experience, what's it's about? First of all, it's always about a largely impacted area, which means that many stakeholders are involved in this kind of projects. It's also a multidisciplinary project. It's not just about drilling a tunnel. There's a lot more to it. Many different disciplines need to work together, and also very specific expertise is necessary to achieve that. And if we talk about big projects, because tunnel project most of the time, when we talk about big budgets, you also talk about many people, and also many risks regarding communication and project control that are popping up. And on the right-hand side of the slide, maybe some of you recognize this, but this is not an ancient picture of the Tower of Babel. But you have to be careful that you don't end up in a scenario like that, specifically for these kind of projects. Next slide, please. So it's all about collaboration and follow-up. I put here a small sketch in the center. Of course, you as a client, you define the needs, what is necessary, for example, for Einstein Telescope to be able to operate. But at the same time, you have a way to achieving that. You have a route to go, so you need to mitigate your risks. And by choosing your location, you know there are 2 sites which are in the running. You also state out the conditions of your project. And in order to achieve that, you have to be very alert on different fields. So first of all, you have to recognize that most of the time the client is not capable of doing the project completely by itself. So you need many other parties that are to be involved. You need engineers, sometimes architects, contractors, facility management, you name it. There are many different experts, etc., that need to be involved in your contract, in your project. So it's important also to think about contract management with all those different parties, and technical management for realizing your dream. At the same time, you need to be very aware about managing and controlling your quality, your planning, and your cost. Specifically, talking about these kind of large tunnel projects, they do have they intend to go out of budget. There are many examples in the past around us where you see sometimes that in the newspaper. So it's very important to have a thorough follow-up of project management and project control. And last but not least, I would say, if you talk about these kind of big projects, you also talk about many stakeholders, both on private or on public side. Public side, of course, we know under the form of permits that need to be achieved. And specifically in an area where you have different countries, the legislation can be quite different. So it's important to know this. And so environment management is very crucial on that. On the right side, there's a small picture about a system that is used by Rijkswaterstaat in the Netherlands. It's called Integrated Project Management, which also has a way of dealing with all these different aspects. And but there are many systems that you can use. Although the most important thing is that you keep in mind that these aspects are important in your project. And I will come back to that a little bit more in detail in the next slides. Next slide, please. So if you talk about the timeline for such a project, for a project like this, achieving it and then getting to your operational phase, as we put it, it's quite a straight line. So it starts with a feasibility and conceptual study, and I think this is where we are right now with Einstein Telescope. But once you have the green light, then it starts with basic detail engineering, execution phase, and operational phase, where many aspects that do have an impact on the cycle as a whole. In parallel, you have to be aware that you also have these permit and expropriation procedures that are going on, and most of the time they start somewhere after basic engineering, because you need to have nowadays quite a good idea about what you're going to do and what the risks are on the environment before you get a permit. And you also at the same time, which is the third branch, I would say, is procurement. You need to think about when to involve certain parties, when to involve a contractor. What is the wisest thing to do for your project? Of course, this is now a straight line, but in reality, it's a circle. It's something that continues, specifically if we talk about tunnel infrastructure, and also for Einstein Telescope. We are not talking about a 2-year lifespan like with our LED television. We are talking about 50 or 100 years or something like that. So we need to think about not only having a project ready in a couple of years, but also how to maintain it and how to deal with maintenance in the future. Next slide, please. So a bit going into focus on these different aspects. Just to highlight out all the things that will also play a part in Einstein Telescope. We need to think about technical management. The first thing, of course, with technical management is the inventarization of the existing situation. And I think the ET test and so on, these programs, ET Pathfinder, it's all about that also. It's inventarization of the existing geotechnical or geological environment, but it's also testing about what is feasible and what is not feasible and so on. But once you have a green light to go with a project like this, it's also converging and make sure that you are converging and not diverging to a final design that corresponds with your objectives. If you talk about technical management for these kind of big projects, you also need to think about staffing. Big projects, many people, many experts. It's not that if you say, okay, we start with this project and we want to start within a month, that you have all of a sudden 100 engineers standing ready for you to do that project. That's not the case. You need to think very thoroughly about what the market is, what you need, and how to deal with that. And at the same time, you also need to involve the right competences for mitigating your risks. Find the right match of people or companies and competences. For example, for this tunnel project, we also have we are setting up a collaboration between Tractebel and Amberg Engineering, who specialized also in tunnel boring, to have all the competences that are necessary for projects like this. Next slide, please. Project control, I've mentioned before, very important. It's using tools, it's using processes to guarantee that your project will deliver on time, within budget, and within the objectives that you want to achieve. So you do that with different tools nowadays. You have systems engineering, which is kind of a multi-dimensional database that links demands, requirements, people, etc. And that can help you get an overview of your project in a way that is much more evolved than a simple Excel will. And I can guarantee you, with a simple Excel, you will not achieve projects like this with this complexity. BIM, building information modeling, also very important nowadays to have digital twin of your asset. And you need to think about, of course, the way how to collaborate between all those different systems, because you have many parties, you have many people, they all work in a different way, they all use different tools, different software. You need to bring that together. So it's really important to have a good setup on that. And of course, project control is also related to planning, monitoring, and cost estimation and monitoring. Next slide, please. Environment management. Although Einstein Telescope will be mainly below ground and quite a bit below ground, there are some places where you need to come above ground. And even for the underground parts, probably also, you need to know what you are able to do, what's necessary to do for permitting, what are the procedures, what is the timeline, who are the stakeholders, who is impacted, how much are they impacted. It helps you to get a triage of stakeholders, and specifically also in the big infrastructure projects in which we are involved. It's always very much about communication and involvement about what you're doing. And sometimes we go that far that we incorporate in our design team stakeholders to make sure that we get a common ground for our design. Next slide, please. Contract management, I said it before, you work with different parties. So you need to think about the ways of collaborating with those third parties. Of course, you will maximize alignment with all these different parties, but of course, you don't have the same objectives always. So you have to see what to do with at the areas where you have different objectives. You need to think about that. You need to think about in your contracts. And the better you do that, the better your project will be. Because if you have a bad connection with contracts, and then it's already a bad situation from the start. And it really helps in the end to have a good idea, a good vision about that. It's also about managing and mitigating your risks in that field, because you need to define who is the most suitable company or organization to take responsibility for some of these risks. And of course, there's nowadays there are now new types of contracts that are popping up in the industry that help you deal with that. So you have NEC 4 contracts that are also used in the Antwerp region and so on. And last slide, please. And last thing is project management is manage the interaction between the teams and the client, very important also, and follow up on your objectives, and also adjustments. We are in here for a long time. It's a long project most of the times. Many things will change, so you need to be able to deal with that. So you have to aim for a balance between some sort of rigidity or a flexible structure and approach to deal with that. And last but not least, I would say it's one of my personal favorites is also try to have fun in your project. You're here running a marathon with many people together for several years. You have to work together, and so you have to also keep in mind the good work and private balance, and have a fun project. And in my experience, if you take some energy and to try to achieve that, to get a good project team on that, it pays off so much in the end, because it's very easy to go to emails and to stay behind and to hide behind contracts and so on, but in the end you don't solve it, the real issues that will pop up. And well, that's it for me. I see I am 2 minutes above time, beyond time. I will finalize now. I hope it was very short, of course. I can talk hours on this subject, but I hope it gives a little bit of insight about what these kind of big projects are all about, regarding management of that, technical management, project management, etc. And well, let's hope that we can get this project in our region.
Okay. Thank you very much for the presentation. Yeah, almost in time. No worries. Then we have our next speaker, Professor Nguyen. You gonna share your own slides, or shall I show them?
Hi everyone. I can try to do it.
Okay, yeah, just a second. Yes, wonderful.
Yeah, do you see the correct slides now? Or do you see it full screen, correct?
We just saw, now we see again. Yeah. Perfect.
Okay, great. Okay. Oops, I don't hear you anymore. I just disconnected. Right. So, hi everybody. So my name is Fred Nguyen. I'm a professor here at the School of Engineering in the University of Liège. And I'll be talking today on behalf of the ET2S consortium. and in particular on the parts which deal with the subsurface characterization, as we have just seen by Joseph Ikmans with his very nice presentation. And I will be basically summarizing a bit what we have been doing. So just to introduce you our partners in terms of the subsurface characterization, that will be, in addition to us, the University of Bonn, NMWP Aachen, KNMI, and NICEF are mainly involved, I would say, in the activities. So the global motivations, perhaps you have heard that already, but the global motivation of burying basically the Einstein Telescope at a depth of 250 meters or so is that we do have in some part of the regions, we do have those softer rocks, let's say, that can actually dampen the vibrations, so the human-made vibrations, and also the natural vibration that are always present, I would say. And if you look at the graph here on the right, you do see that what you do see is basically, let's say, the magnitude of the vibration. Sorry, as a function of depth for a location located in Terzit. And so you see that basically after a few tens of meters, you suddenly have a drop of the magnitude of those vibration with depth. And so this is typically the condition, sorry, that we're trying to reach in the subsurface. However, when you start going deeper, then of course you face other challenges, right? And one of the challenges is to basically find some suitable rock in which you can actually host the subsurface caverns, not only the tunnels, but those big rooms where the interferometers will be located. And you can also face, in particular in the area, places where the geological layers will be faulted and folded. And so where you might also find the presence of zones which have been dissolved by water. And so where you, for example, would have a strong groundwater flow, which is important to understand prior to basically setting up your civil engineering problems in order to avoid issues afterwards. And we all know that basically when we go from the surface where we have a lot of information, you can look, for example, in an outcrop and quantify a lot of information that was done by Aachen, like the fracture network and the orientation, their densities. When you go deeper, 100-meter depth, you might find just a couple of boreholes in your area. And when you go 300-meter down, then you might have to place a new borehole to actually have information. And what you get out of it is actually something that looks like this. It's a rock course on which you can actually perform different type of measurements, but it's quite a small amount of information that you would actually extract from the subsurface. So the ET2SMEs project, the objective is basically what has been said before, but by Joseph, is basically on one hand to gather all the information that actually exists on the subsurface and to gather new data. And this new data comes in the form of new boreholes. So this is the borehole of Cuttesons that you actually see here. But we also gather geophysical images, and we of course measure some parameters, hydraulic parameters, geomechanical parameters in the lab. And we basically use all that data to feed models, and I think you will see some of them in the presentation of Florian Wellman after me. And of course, the topography is something that can be easily integrated and is well known. But then you have to understand how the geological layers actually interact with each other in the subsurface and how they are displaced, for example, by faults. Not only do you have to represent qualitatively how those geological layers are, but you also have to quantify their parameters. And so, for example, what is their density, their porosity, or the rock strength, for example. So I selected a few project results. So since we're quite limited in time, I just have a few of those here, and not are all in details. But what we have completed so far in terms of drillings is we have now 2 boreholes completed. One in Cuttesson, you see here just at the border between the Netherlands and Belgium, and one in the Netherlands, in Bad Holt. So this is the example of the results of Cotteson. You see Alessandro here, which is testing seismic centers at depth to basically measure the amount of vibration that you see here on the screen. And at the top, you see the results of the geophysical logging. So you see here a nice image on the rock where you can nicely see some fractures in the more in this area in the rock. You can see it better in the acoustic logs, and so you can extract a whole amount of information from these data to understand how the subsurface actually looks like a few hundreds meters down. Together with this borehole images, we also gathered geophysical data at selected locations. And so this is an example of one of the sites that we are studying in more detail. It's called Ombu. What you see here are basically sensors which are placed at the surface on the fields. It's basically electrodes where we send in electrical currents and we get back the potential differences and try to then understand where the current is actually flowing the subsurface. That allows us basically to reconstruct images of the subsurface, which would mimic what the geological layers would be like. And so you see different cross-section of that allow us then to reconstruct the geology. In the particular case, we see that for example, we can correlate two types of formation in this case, the Wye formation and the Famenia formation, and we can also then use this image and we know what type of parameters is associated with it thanks to the borehole and the outcrop data, and so we can use them to basically extrapolate the information. So here you will see now here Peter Kukla, Frank Linde, and all the team from Aachen actually jumping around the Terzit sensor. So they're as director of the university, and so we also busy with measuring how basically vibrations attenuate in the subsurface and understanding which type of infrastructures actually plays a role. So typically, you might find a lot of windmills nowadays in the area, and so we set up a campaign, passive seismic campaign, to basically measure how, as a function of the distance, basically the magnitude of vibration would attenuate as you walk away, let's say, from those windmills, but also when you go deeper down. So that's important to understand, so that we are sure to basically respect also the Einstein Telescope specification in terms of vibration. So this makes this project quite unique in that regard. You'll see more information about this. I won't say too much, since I think Florian will show a lot about this. And so we basically feed all this information to build up a 3D geological model in the subsurface, and then we can see where we can actually put where we could optimally, let's say, put the Einstein Telescope in the subsurface. Also, a big part of the project is related to groundwater resources. So in the area here, what you do see is so the circles represents where you actually extract groundwater, and it's basically from, let's say, the upper aquifer, and so the area of the circle is proportional to the amount of groundwater that you actually extract. So we don't have much information, I believe, from the German point. That's why actually it's reddish. But it's sort of further away from the area that we are currently studying, so that doesn't influence so much. And so basically this is a system that's being exploited for its groundwater, and so we know that we're quite rich in terms of groundwater resources. What you see in red here is the area that's going to be modeled by the project. And so you basically have a system where you have water, you pump water out of it, and the red part is basically the boundary condition of the systems, which basically corresponds here to the Meuse River, for example. And so what we do is, you see Aachen is here, Maastricht is here, and Liège is here. We basically take the 3D geological model and we translate it into a hydrogeological model. That is basically, we assign them with some hydraulic conductivity values, some porosity values, and we then allow some groundwater to flow into this porous system right? And so what you see here are now the hydrogeological layers, the different ones that are going to be represented. And the animation now shows you in blue is the water level in the ground, right? The groundwater level. And the sort of the light blue lines show you the trajectory of the groundwater flow. And then we can use that such model to not only optimize, let's say, how one would use the groundwater resources that is useful for the whole cross-border area, but also to understand how the Einstein Telescope will impact those groundwater resources, for example, during the construction phase and afterwards, if that has any impact during the exploitation phase, let's say. So in terms of follow-up activities, so you've seen that we've done quite a lot of field work currently, so but we still have a big seismic campaign. So this would be a seismic reflection lines, so 40 kilometers of seismic reflection lines from which we have received offers now. And so that would actually allow us to get more information about the structures. So right, so the geophysical image that we got so far gives us a lot of about the nature of the rocks that we were having into the subsurface, and now we will gain more information about really the geological structure, so the faults, how the layers are inclined, and so forth. We have also a couple of boreholes to drill and hydrogeophysical testing to do in those boreholes to get a sense of their properties at the scale of a borehole. And basically to also, and that's a big task, to integrate that into cross-border model and to also validate, of course, the models using different independent data sets. After that, one of the final output is going to be some cost updates in terms of civil engineerings that we can use then in the bid book then for the Einstein Telescope in the area. And I think I'm done with my slides. And yeah, that's it. So thanks a lot for having me, and thanks a lot for listening.
Thank you for your nice presentation. Actually, you catch up sometime. Really like that. Thank you.
Yeah.
Then I would hand over to our next speaker, Dr. Schlögl. You want to show your slides yourself, or shall I?
Yes, if I can share my screen, it would be nice.
You should be allowed.
Okay.
Yes, we see something. Yeah, perfect.
Let me see it. Yeah. All right. Yeah. Is it fine this way?
Yeah, wonderful.
Great. So my name is Romy Schlögl. I'm a researcher at the Space Center of Liège. So I'm not directly related to the ET2SMEs project. Actually, I'm a research fellow financed by the European Space Agency. And actually, I created my own project related to the remote sensing analysis of the ET2SMEs region, while it was not actually included in the ET2SMEs, the current ET2SMEs project. So just to give an overview of what is actually remote sensing, it's the process of detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation at a distance. When we speak about Earth observation, actually it means the information collected from Earth observing satellites or aircraft, or can be also drones. And there are different types of remote sensing techniques, but the main phases are actually the first one. We have this energy source or illumination, which can be coming from the sun. And this emission can be, which is giving an energy to the Earth. So this interaction of the electromagnetic energy with the Earth's surface on the target, it's actually resulting on a reflection in a way which is depending on the properties of the target. And then we have the sensor, which is recording this emitted or reflected energy from the target or from the Earth, which actually consists of the data input that we get. And then we have the transmission of this data processed to the ground, which is actually our data output. So as an expert, we of course analyze this kind of data and we interpret it. So we have passive and active sensors. The passive one is a sensor which measures the energy which occurs actually naturally. So the source is the sun, and it gives you an information of the spectral reflectance on the ground, for instance. And when we speak about active remote sensing sensors, we are here considering of the own source of energy, which is actually given by the satellite in itself, for instance. And for instance, we have this technique which is called synthetic aperture radar interferometry, which I'm gonna speak now. So this is actually a technique that I'm using currently in my own research, which actually uses, when we speak about differential in SAR, it uses two different SAR images of the same area, which is actually acquired at two different times. And it allows us to calculate the phase difference. So when I speak about phase difference, actually in the signal that we obtain, we have a contribution which is coming from the water vapor, which is in the atmosphere. We also have a contribution of the topography. We have to consider also the orbital contribution because of the satellite path. We have also an ambient noise, which is actually due to the vegetation, which is present on the ground on our target. And here we want to know what would be a possible deformation of the ground, so which is the phase deformation which we want. And this phase deformation is calculated with this technique, and it allows us to estimate ground deformation of the order of millimeter to centimeters. And this will be actually calculated along this invisible line between the targets on the ground and the satellite. So we need to think in one dimension. And this is also according to the properties of our SAR or radar system that we have in space. But we will calculate this difference, which is actually the difference between the satellite ground distance. So it's a really powerful technique because we can cover a really large area. So for instance, the full Einstein Telescope area. And we have a sensitivity to vertical deformation, which with accuracy between millimeter to centimeters, according to the technique, the INSAR technique that you are using. We can have the evolution over time, see if there are some deformations which are actually happening. But there are also some limitations. And one limitation would be actually due to the topography of the area. If we have some hills, sometimes the line of sight is not actually covering some parts which are in some other sides of the mountains, for instance. So there are some SAR properties that you need to consider if you want to check on some slope deformations. We also have some decorrelations of the signal. For instance, if we have some snow, some intense rainfall, which are inducing some erosion on the soil. We also have the influence of the vegetation. So for instance, the target that we want to focus on, is it like a tree? Is it like a soil which has changed? Or this scatter can also change over time. And we also have some tropospheric effects that can also influence the signal. One other limitation would be also the velocity of the process that we want to monitor, which can be also too high to be detected by this technique. So if I want to focus on the area, the transborder area between Belgium, the Netherlands, and Germany, so there are some multi-temporal INSAR techniques which are used in those countries. For instance, in the BGR, they are already creating this average velocity map using some Sentinel-1 data and a technique which is called persistent scatters interferometry. As you can see here on this slide, actually it's only covering the period between 2014 to 2019, so it's not up to date. But it gives you an information on the location where there can be some slope deformation. In the Netherlands, there is another platform which is also used and which was developed by SkyGeo, which is really interesting because you can actually also zoom in some location and extract some time series to see the evolution of slope deformation. And for the Belgian side, it's going through the border. So we also have some information on the Einstein Telescope area. So for instance, as Frédéric was also mentioning, the Hamburg area. So here in that location, there will be a new borehole, and we want to know if after pumping in this borehole, we will see also some evolution of the ground over time, and this can be also measured by this technique. So on this website here, for instance, if I check on one point, I can see the evolution of this deformation on that specific location. Here, to give you an order of magnitude, we have more or less 4 millimeters per year on that specific location. So yeah, quite moving. We can see it's significant enough, but well, it's not that much, right? So if we check on the Cottesen area that we also mentioned previously, where this borehole was already drilled, here we see also some green points, so those coherent reflectors which are also monitored over time. And here, we have a velocity of 1.5 millimeter per year, which is pretty stable in that location. So what I want to do also in the frame of my own project is to cross this information, so the persistent scatter interferometry, all those points that I can have over the borders, as you can see on the figure here, with the geological context and with some specific fault structures, because I want to see if there is an influence of those faults on some potential deformation that I can measure through the PSI. I've also used another technique. So before I was speaking about PSI, which is one specific INSAR technique, and now I will speak about the multi-temporal small baseline subset time series, which is actually an algorithm which was developed by at the Centre Spatial de Liège and with some other collaborators also based in Luxembourg at the European Center for Geodynamics and Seismology. So they also helped me to collect all the data in a cloud covering the Einstein Telescope area. As you can see here, I was able to retrieve the ground deformation rates in the up and down direction and in the east and west deformation. So as I was speaking before, with INSAR, we only have the deformation in one direction, in the line of sight direction, but then you can reproject it in the directions you want. And here it's interesting to see that, according to the reprojection, you don't see, the same things. What you can see, for instance, is on some mines, of course, there are some down deformation. It's Elfdorf in Germany, for instance, which is pretty visible in the INSAR signal. And if I focus on the area of the Einstein Telescope, here I also superimposed the fault lines from the Belgian side. Now I have to include also those in the Netherlands side. I can also see some signal, which is also visible. So what is interesting to see is, of course, here in the Belgian side, we see that it's more like a dawn deformation, a maximal dawn deformation, which is visible. While if I check on the east and west deformation, we can see in the southwest of Aachen, this deformation, which is basically due to the Rhine gravel, which is also visible. So this is just to show you this kind of result that we can see. And of course, there are also some hotspots area. Here we can see, for instance, red spots, which are in most of the cases, they are located in some mine activities, or where there are some big change in land cover, for instance. It might be also due to change in the crops, or pumping area with subsiding surfaces. So in those locations, or specifically in Hambourg and Cottesen area, I also want to combine those results, this MS-BAS results, with the proximity to the fault lines, the main fault lines, to see if those faults are stable or not, because it can be also interesting to know this beforehand, before the construction of the Einstein Telescope. And this is coming to my conclusions, actually open to discussion, of course. So I wanted to show you that there are some platforms existing to control slope deformation with INSAR at national scale. Except for Belgium. Actually, for Belgium, it's more currently with the Terrascope platform, it's more focusing on the optical monitoring. So there is no INSAR processed in a continuous basis, let's say, or doing time series to see deformation. But in the future, we will have this European ground motion service. So this might open also some new perspectives. The problem with this is that either this new service or the current platforms are doing the monitoring in a continuous or up-to-date manner. So as you have seen, also the monitoring is ending either in 2019 or in 2021. So we don't have the current and the up-to-date with the new Sentinel acquisitions currently happening or happening in the future. I also wanted to precise that the expert knowledge is mandatory to interpret well this remote-based information, because if we deliver all this to the stakeholders directly, they can be misinterpreted results, which could also lead to some problems in the future. And we also need to consider that there is also the need of ground-based measurements, either by permanent GNSS or by IGRS, so this integrated geodetic station, which are actually developed by the TU Delft, some colleagues there, to help validating these INSAR results. So thank you very much for your attention, and I would be happy to answer questions in the future.
Yeah, thank you for your presentation. The question is to all the participants. If you have a question, use the raise hand function, type it in the chat, or unmute yourself and shoot. Maybe if I can take a first question, what was this object on the bottom right of your last slide? Is this one of the ground-based sensor, or?
Yeah, it's the IGRS station. Actually, it's a combination between corner reflectors with GNSS station with a leveling, which is actually taking some like continuous monitoring on the ground, and also having this artificial backscatters, which can also give a right signal to the satellite to be tracked over time.
Okay, thank you. More questions? Otherwise, we also have later the opportunity for further questions. Thank you very much for staying very well in time. Then I think we proceed with the next talk. Yes. Perfect.
Can you see me already?
Yes,
and
we
here?
see you already. Yeah,
okay.
we still see the gray surrounding of the program, but I.
Oh,
yes.
I'm sorry. That's
Yeah, the last time in the testing you managed it. How did you?
Oh, okay.
Same
Maybe
like
let's
before.
try.
Yeah.
Let's try. Let's try. Maybe like that. Or did it change something?
Not yet.
No.
Well, when we tested it before the meeting, it worked. I do the same, whatever it was.
Now?
Yes, perfect.
Okay, fantastic. Thanks a lot. Okay, so yes, welcome everyone also from my side. I am Professor Florian Wellmann from RWTH Aachen. And I'm actually a professor in computational geoscience and not so much in virtual environments, but I was asked to give you a bit of an insight into virtual environments and how we relate to this in the context of the Einstein Telescope project. So I'm sure some here actually are more experts in this virtual environment part, but I try to make a bit this link maybe to the data we have, to the models we have, and how this should be or could be combined in the future to get some insight into the subsurface that we need in the context of this project. So yes, what are virtual environments? Well, what we have in mind, from a very simple point of view, is that we have some sort of maybe a geological structure, any structure, and we want to interact with it and see what happens in 3D. But let's actually, just before we look into this part, let's take a step back and actually look at a bit more conceptual viewpoint of what virtual environments actually are. In a very broad sense, we can say generally we look at something which we could call virtual representations of some sort of a real world object. This is here from a different field a bit, of course, but we have here, from the energy sector, we could say that we have some sort of a drill rig or something, and we have it in reality, and we have a virtual representation. And we try to get those two sides together so that we can actually interact and work with this virtual representation and see the effects in the real world, in a sense. This is something which also leads to concepts of real-time data assimilation, so integration of information to make better predictions. And some of the central characteristics that you will find in this context are related to connectivity. So basically to have your virtual environment somehow connected to your data input that you're getting in the real world. Aspects of homogenization, which refers to a bit more on the technical side to data and how you are interacting with data in both the real world setting as in this virtual setting. What is sometimes called smart adjustments. So basically that you are able to make adjustments in your process based on the results of your simulation or your virtual environment, basically. And also that you have some sort of a digital trace of what you are doing. So basically some way to go back once you did an analysis, you want to see why this came to be, in a sense. So you want to have an accountability, in a sense, through your digital virtual environment. And it should be also modular, in a sense that you can combine different aspects together, different data types, different simulations, and combine them to get basically to a final result in your virtual environment. And all of these concepts are quite often also referred to as what's called digital twins of the real world. This, of course, also combines all the aspects of simulation and prediction. In our case, what we look at in the current state, I would say, are two components of this big field. And two things that we would like to combine. One of them is actually the information about the subsurface of geology and rock properties. And we've seen already fantastic examples before in the talks before. Basically the aspects that are then relevant for groundwater prediction or also the tunneling predictions or the engineering prediction. And we want to combine this also with these engineering aspects and the actual construction that is happening and the objects that are built underground and above ground potentially as well. So let's see briefly how these things could be combined in a very, like geological modeling in 2 minutes. This is of course not the area of the Einstein Telescope. This is somewhere in the Pyrenees. But you see basically this is a typical rock structure in an orogenic setting here. We see we have these different rock layers. And of course, we can see this sometimes nicely in mountain belts. We can look at the rocks and we can identify them. The problem is, of course, now in our region here that we talk about, we don't see this. This is all below ground, right? And the difficulty is that we cannot directly see it to look at all this complexity. So we need to substitute, basically, we need to find ways to look into this subsurface. And we have all of these different scales of observations. We have some areas where we see significant changes of rock properties. We see, if you zoom in a bit, we see some smaller sections where we see maybe similar rock type, but different properties. And this goes on, to very small scales. So we cannot see it. What can we do? Well, what we do, you also already saw this in the previous talks, of course, is that we take information from, let's say, for example, boreholes here, where we have a lot of direct observations and indirect observations in seismic measurements. I'll show some more examples of this in a minute. In the end, the aim is to reconstruct then this picture of this geological setting, of these major geological interfaces, based on all of this partly direct but very sparse, or indirect and more widely available information. So what we want to end up with is a representation of geological features. We can think here of aspects like fault zones, so discontinuities in the rock structure due to fracturing, what we've seen also in the last talk. And we have maybe some relevant interfaces between different geological layers. But if we also zoom inside, then we also, with a smaller scale, we also see that we have maybe properties, rock properties inside the subsurface, which are also, of course, not completely the same everywhere within one layer, but which are also changing due to local variations in this geological system. Let's see a bit now what this means in the context of the Einstein Telescope after this 5-minute introduction to geological modeling. If here, just a movie that one of our researchers made, Niels, who's also working, Niels Studalla, who's also working in the Einstein Telescope project. And this is just a bit of the setup. We've seen this already before in a couple of the examples, but you know that the main challenge is basically to find the best region now where we can place, to start with, where we can place this telescope object. And just to give you a bit of a sense of scale, I think it's quite nice to see here, when we look at the scale of the cities around it, that of course we're looking at a major structure and would like to see how we can best place this in the first stage right now. So what we do is we need to characterize the subsurface in this entire context. And this comes together in these aspects of geological modeling and geophysical investigations. We've already seen here an example of this model before. This is an actual representation of the features we expect in the subsurface below this region, in the Einstein Telescope region. And we combine different aspects from borehole data, profiles, maps, and so on, integrated in this 3D structural setting. So this is, of course, a difficulty in itself. What I'm not going to talk about too much about here on the technical side, I think what is really interesting to think about first is actually the challenge of data integration when we think about these virtual environments, in a sense. So we've already seen this again in the talks before, that we have these different types of data sets already on the geological side when we look at integration of borehole data, geophysical measurements, and geological knowledge. And the big challenge is to combine this then with aspects of the more civil engineering aspect of the project. Also something which I'm going to mention, but this is maybe best seen with a couple of examples. We've also seen already something about the borehole, the examples before. And again, I'm sure many of you have seen how this works, but just to give you also a bit of a more schematic idea. If you think of a drill rig somewhere, we're drilling in these sites that we've seen in the last presentation already. What is actually happening, of course, is we are drilling down to this target depth, and then we are extracting information in cores, basically, of this borehole. And inside of these cores, we have a lot of precise information, but of course, at a very small scale. Think of this borehole as, in the decimeter range. And then we can go ahead and also take geophysical measurements in these boreholes. And we see here an example of a wireline log represented, where we take measurements and get some more information in the surrounding area of this borehole. So this gives us very precise information, but also only at very dedicated point in space, in a sense. Now, if we need to combine this, we'd like to extend this now to a wider range. And this is already where we've seen examples of ERT before. And Fred and Nguyen already mentioned the seismic campaign that is going to be part of this study as well. And what is happening there is that we are basically emitting sound waves into or seismic waves into the subsurface. And where we have some important features, changes of properties in the subsurface. This leads to a change in the distribution of the seismic waves. And this is something that we can then observe and measure at the surface again in sensors, represented here, basically placed at the surface. And combining all of this information gives us, again, some of this more partial information in the subsurface. Now, why is this all relevant? Well, in the end, the point is that we put all of this information somehow together into a geological model, but you've seen now a bit the complexity of the model with all these faults in a large scale area. We're talking, of course, about tens of kilometers. Then we have some very precise information, high resolution on a millimeter scale or even below in boreholes. And we have these seismic measurements that we have partially in space and ERT data. And we believe that one really big challenge here is to get all of this information into one environment, into one virtual environment, where we then see where we have information. We can see the interpretation. We can maybe even make interpretations in this 3D virtual space, which guides us a bit more our understanding of the subsurface to be able to make better predictions. I have here one example of a tool where this has already been partly tested by Terranigma Solutions. So this is a prototype example here of one of these setups which already integrates some aspects of this virtual environment. But you see here that we have an example of this model that we saw before. And we can see the geological structures inside, and we can see how we can move into this object already, into this 3D space. We have ERT data in here, so this is one of the other data sets we've seen before. And the challenge, of course, would be to get more information in there to help us gain a better understanding of the subsurface in the ET region. Then I mentioned already this link to civil engineering. And because what we've seen right now was the geological structure. A lot of this is not very well known, or we need to infer the position of these structures from our measurements. If, on the other hand, we do a civil engineering project, we plan this ahead, and we know, of course, quite well what we will build and what is actually there. So this is a different world, and in this virtual setting, we can bring those two hopefully together. At least that's one of the challenges here. This is an example from a Geology Technologies report on trends in architecture, engineering, and construction. And I think it gives a bit the idea of where this way is going. We see here a lot of pipeworks in an underground system here. We see actual pictures behind it, or a view basically on the reality. And we see how this real setting basically and this expected piping here is combined in this virtual environment. So the big challenge will be, we think, in this context of the ETES project, to bring both of these sides together. So on one hand, this aspect of geology and geophysics and all the data that we integrate into these subsurface geological models, with these engineering aspects that we can then, of course, also see when we have the tunneling projects, for example, that we see where we expect the tunnels to be, in which geological setting, which properties do we expect, how will this influence the groundwater, and so on. A very small note on technologies. That's something which is really, in terms of expertise, that's outside of my expertise, but of course, just to give you a bit of an insight of what is available and why also this is maybe something that we can do now, that we can take the step to combine geology and engineering here. Because we've seen in the last years, as I'm sure all of you are aware, we have seen a surge in developments on the hardware side for virtual reality glasses and also augmented reality glasses in all kinds of varieties, mostly for gaming, but also a lot in engineering, in architecture, in serious real-world applications, of course. The most important point with all these developments is that we've seen the costs going down significantly. So this is something which used to be in the more specialized market. It's now really in the consumer market segment. And at the same time, we see all these developments on the software side. So I already mentioned one software, Unity, before, which is a game engine, but also used a lot in real applications, let's say. Unreal, another one. Blender is a 3D modeling engine. Autodesk, Sketchfab allow you to generate these models as well. So there's a lot of software right now already available out of the box, in a sense. The question is, in the context now of ET2SME maybe and e-test in general, or the Einstein Telescope, how can we combine all of these elements to get a better insight into the subsurface and the combination with these technical and civil engineering aspects. Mr. Meyer already mentioned at the beginning the ET technology sheets. So if you want to see a bit more about where we see requirements for the developments, this is in the technology sheets on simulation and modeling. You can see down here there are two segments on collaborative research in joint virtual environments, and also one on challenges in geomodeling and geobim integration. And what you see here on the left side, earthquake, ambient noise, and wave propagation simulations also add on to this aspect of geological modeling, property estimation, and then also simulations and virtualization. Okay, thanks a lot for listening. This was then my contribution here. I hope we could give you some insight, and of course, happy to answer any questions there as well.
Okay, thank you very much for your presentation. Then we come to the networking part now. I will open up to breakout rooms now for all of you to join. These breakout rooms, you're free to jump between this one, this is the main room, and the two breakout rooms. The two breakout rooms have a topic name, so where it should, or it will be more focused talks about the talks we just heard about the connected technology. So remote sensing and virtual environment and simulation are the two rooms. Feel free to switch between them. You find them also in the gray bar on the bottom. Once you are in a room where you can, on the right bottom side, you have this leave, and then you can decide if you leave the hall or you just leave the breakout room, then you go back to the main room. So, yep. There we go. There should be a window now in the center of your screen to join the rooms. Looking forward to the discussions, and thanks again to all the speakers. If you have questions now, go to the rooms, discuss. Looking forward to it.